Hello everyone, my name is Kara Hettinger and I'm a master's student in the Department of Land Resources and Environmental Science at Montana State University, Bozeman. There I am working with Tim Seipel and Perry Miller, and today I will be discussing our work on the comparison of integrated weed management strategies for creeping perennial weeds here in Montana. Perennial weeds are one of the biggest areas of concern for organic agricultural production in the state. Here we're looking at the results of a 2012 survey that was sent to organic grain producers throughout Montana, asking them to list weed species of highest concern for them. In a sublist of perennial weeds, you can see that Canada or creeping thistle and field bindweed were most often listed as occurring on farms, and when they were present on farms, were often listed as hard or impossible to control. So what exactly about these two species makes them so difficult to manage? First, they have this creeping root system, which is made up of laterally spreading roots, which allows field bindweed and creeping thistle to access nutrients and moisture, outcompeting weaker rooted crops for these needs. Additionally, field bindweed is a vine, meaning it can choke out crops as well as become a nuisance for farming equipment. Both creeping thistle and field bindweed also have an extensive rootstock. This rootstock acts as an energy store for the plant, so even if they are disturbed by something like tillage, they can often resprout readily from the energy they have in these roots. And finally, for field bindweed, they have quite long-lived seeds, so even if you have successfully removed existing plants from a field, it's highly likely that there are viable seeds still in the soil bank. Creeping or Canada thistle is difficult to manage in very similar ways to field bindweed. As I mentioned, they have these rhizomatous or horizontal roots, which can put out lateral shoots, known as propagules. These propagules can then form second flowering parts and quickly colonize a field. Additionally, these propagules are examples of the extensive root system of these two plants. Here is a photo I took in the field in this past summer of 2021. You can see that a Canada thistle root was severely impacted by tillage. However, it had enough energy stored in its roots to allow the resprouting of this plant you see here. So very, very impressive plants with their root system. So it is understood that thistle and bindweed are difficult to control in organic settings. However, it's also been shown that utilizing an integrated weed management approach can be successful for managing these two species particularly. Integrated weed management is simply the combination of multiple techniques to manage weeds. And today, I will be looking at how a combination of different mechanical and cultural controls can start to manage both thistle and bindweed. In the first study today, I will be talking about field bindweed. This was conducted at the Western Agricultural Research Center by Zach Miller and Kirsten Hubble, and they had two major research questions for the study. The first being which cropping system treatment would best manage field bindweed, and if the intensive tillage regimes within this treatment would significantly impact soil health and quality over the course of the study. To accomplish this, they set up 10 different cropping system treatments for this study, and they were organized on the spectrum from least to most soil disturbance. So at the top of the soil disturbance spectrum, you have two treatments that utilized frequent and intense tillage options, as well as a fallow. At the lower end of the soil disturbance spectrum, with the least amount of disturbance, you have both conventional and organic alfalfa. The conventional alfalfa being sprayed with glyphosate in the first year of the study. And in the center here, you have rotations that sort of fit within this gradient of soil disturbance. The ones at the top receiving more frequent tillage and utilizing different cover crop wheat rotations. The ones at the lower end seeing a reduced tillage or grazing treatment, and again, utilizing different crop rotations. As I mentioned, this study took place at the Western Ag Research Center out in Corvallis, Montana. It took place from the fall of 2017 until harvest of 2020. In this diagram, you can see 3 replicates in blocks A, B, and C, with all 10 treatments randomized throughout the blocks. Now moving on to results. Here we're going to start by looking at densities of field bindweed by treatment. So these are counts of field bindweed. There's sort of a lot going on in this graph, but I'll explain some general trends. Here, with the highest densities of bindweed, you can see both livestock grazing treatments, treatments that utilize cover crop rotations, and annual cropping treatments. And you can tell that these had the greatest increases in bindweed abundance throughout the course of this study. At the lower end of this graph, you can see that intensive tillage and both alfalfa treatments kept bindweed abundance low. And in some cases, there were no field bindweed in these plots. So from densities of field bindweed, we can use those numbers to calculate how populations increased or decreased throughout the course of the study. And again, we're looking at these treatments on a gradient of least to most soil disturbance, with our intensive tillage treatments at the top and our conventional and organic alfalfa at the lower end of this spectrum. So here we'll be looking at the population growth rates of bindweed from 2017 at the start of the study to the end of the study in 2020. Any negative numbers indicate a decreasing bindweed population, with positive numbers indicating an increasing population. Values near 0 show a stable bindweed population. Right away, you can see that both intensive tillage regimes showed significantly decreasing field bindweed populations. At the lower end of the spectrum, though, you can also see that conventional and organic alfalfa also had decreasing bindweed populations. Most of our intermediate treatments in the center of the soil disturbance spectrum had increasing populations of field bindweed from 2017 to 2020. So our second part of the study was to see if intensive tillage, in fact, lowered soil health and quality over time. And we did find that there were no differences in nitrogen, phosphorus, potassium, or organic matter between our treatments. However, when we looked at average soil stability, we saw that tillage did in fact lower soil stability when compared to these 8 other treatments. So although field bindweed was managed successfully with intensive tillage, it was at the cost of a decrease in soil stability over just 2 years. Now moving on to a study that looks at creeping thistle, we hope to answer which cropping and tillage combinations would best suppress this plant in organic farms. To do this, 8 rotational treatments were created, and these were applied at 2 research farms and 2 collaborative farms in the state of Montana. Rotations 1, 4, and 7 were applied at our collaborator sites, with all 8 rotations being applied at our research sites. In today's presentation, I will highlight the results for the first 3 years of data from the Central Ag Research Center and the first 2 years of data from the Fort Ellis Research Farm. Briefly, our sampling included collecting biomass and density of both thistle and wheat, as you can see in the photo to the right, as well as collecting biomass of non-target weed species. We did this by collecting 6 1 by 1/2 meter squared sampling frames in each plot. From there, we are able to look at things like thistle biomass. Here, we are looking at thistle biomass by crop type in the first 3 years of this study from the Central Ag Research Center. You can see in the first year, from 2019 to 2020, there was a general increase in thistle biomass. And that is likely due to the fact that thistle had time to establish from year 1 to year 2 of the study. You can also see a decrease in thistle biomass in 2021, most likely due to the prolonged drought we had this summer. When we do start to look at thistle biomass by crop type, you can see some general trends starting to emerge. Here we have alfalfa, and we can see that especially from year 2 to year 3, alfalfa, so rotation 1, our competitive perennial crop, kept thistle biomass lowest at the Central Ag Research Center. And this is especially true when looking at 2021, so the box is in blue. You can see that alfalfa, when compared to our less competitive cover crop, or pea, really kept those thistle populations lower. We can also look at crop biomass to tell a similar story. So again, we see an increase from 2019 to 2020, and a fairly sharp decrease in 2021, again, due to that drought. So even in drought year, alfalfa had the highest biomass of all crops. We can see that fairly plainly. And when remembering the graphic of thistle biomass, we can see an inverse relationship, with alfalfa having the highest crop biomass and the lowest thistle biomass, and the opposite being true for our less competitive cover crop, pea, and triticale rotations. A similar story is playing out at the Fort Ellis Research Farm. Here we're looking at the first 2 years of data. Again, we can see that decrease from 2020 to 2021 in thistle biomass, again due to drought. But we can also see that our rotation 1, as well as our competitive grain rotations 2 and 5, kept thistle biomass relatively low in this second year, especially when compared to less competitive pea rotations. Crop biomass is a little less telling of this story. You can see the decrease in 2021 due to drought, and you can see slightly that alfalfa, barley, and triticale have higher biomasses than the pea, but certainly not as stark as the presence of thistle. So in conclusion, we are beginning to see that perennial cropping systems such as alfalfa do keep perennial weed abundance lower. Additionally, we saw that intensive tillage regimes kept perennial weed abundance low, but it was at the cost of soil stability over just 2 years. Additionally, annual cropping systems, ones which utilize cover crops back-to-back, or leguminous species like peas and lentils, had higher perennial weed abundance, and that is likely due to their weaker root systems that are just less competitive with these perennial weeds like thistle and bindweed. However, most importantly, we are noticing that it's vital to manage these populations of both thistle and bindweed while they're small, because once these species get established, their creeping root systems allow them to really take over a spot locally. So with that, I would like to thank Tim Seipel, Perry Miller, and Chris Larson at MSU Bozeman, as well as Zach Miller, Kirsten Hubble at the Western Agricultural Research Center. I'd like to thank Pat Carr at the Central Agricultural Research Center, as well as the Deacon Bailey and Heimbaugh Farms for their participation in the creeping thistle study. And finally, Dan Chichinski, Emma Kubinski, and Tyndall Overson for all their help in the field this summer. And I look forward to answering any questions you all might have. Thank you.